All right, the next topic for discussion is within mensuration is diagonals of a cube or a cuboid. Let's talk about that. In the last two episodes, we did see the volume and the surface area of a cuboid and cube. And just a quick refresher, a cuboid, all the sides are rectangular in shape. In the cube, it's all the sides are square. So cube is essentially a type of cuboid with square shapes. And for both of them, cube and cuboid, if you see the two edges, all the edges will always interact at 90 degrees. Always remember that. And hence, we can apply Pythagoras theorem. And that is going to be the foundation of this episode, this topic, which we will use the Pythagoras theorem to calculate the diagonals of a cube or a cuboid. So let's get started, and let me just change the color on this pencil. Okay, all right. Okay, so I've copied some sample visuals for ease of understanding. These are same visuals or different visuals conveying the same message, and some of them are better than others, so don't get confused with too many visuals. Okay, so what do we see here? I put two cubes. This is a cube, and oh, the color did not change. Hold on. Just give me a minute here. Okay. So this is a cuboid, this is a cube, and here we have a cuboid. Okay. So it doesn't matter whether it's a cube or cuboid. For the sake of understanding, we can mix and match and talk about them interchangeably. So if you see these visuals, and we're going to talk about the diagonals, there are going to be potentially two diagonals. One is this diagonal over here, the short diagonal, this one, the short diagonal. That means it's joining the same sides. It's the diagonal that is joining the 2 points of the same side. Same face. So if you see at the bottom, this A and the point behind, I think it's F, it's written as F. It's on the same side. It belongs to the same side. And that's called the shorter diagonal. In some textbooks, you might also see that it's called as a face diagonal because a cube and cuboid have 6 faces or 6 sides. And this shorter diagonal is a part of the same face. It just joins the opposite points of the same face. Face is nothing but a side or a surface. It's the same thing. Different words meaning the same thing. And the other one is a longer diagonal. If you see here in this one, this is a longer diagonal, this is a longer diagonal, and this is a longer diagonal. Okay. If you see here, the longer diagonal is going to be a diagonal which cuts across two different surfaces. For example, this point A belongs to one side at the bottom, this on this one, and it connects to the opposite side. If you take this G, I think it's not written properly, but I think it's G. If you take this G, this belongs to this top surface. So what we are essentially doing is we are taking a point of a vertex at the bottom surface, and we are joining the diagonal vertex exactly on the opposite side, but on the opposite surface of the bottom. So this is the bottom, and this is the top. Okay, so whenever we join this diagonal like this using two different sides of the opposite side, that's called as a longer diagonal. And as you can see from the visuals, this diagonal's length will be longer than this one. Okay, and this is also called as body or space because it cuts across the body or it cuts across the space, giving it kind of a three-dimensional image. Okay, so just remember that shorter diagonal and longer diagonal. And since we have got two diagonals, we'll be calculating we'll have two kind of calculations, one for a cube and one for a cuboid. And typically, if you remember this longer, it's a good thing because in the exam sometimes they might ask, which I'll be solving in the next episode, that calculate the longest pole or calculate the length of the longest line or pole that can be inserted in a cube or cuboid, and that means you should know that they're talking about longer diagonal. Just as a side note on that one. Okay, let's get started. Okay, let's talk about the shorter diagonal first, and that too for a cube. Okay, I mean, we know in a cube all the sides are equal because it's a square. All the sides are square in shape, so all the sides are going to be equal. Okay, that's we know. And we're going to talk about the shorter diagonal, that is the diagonal A. This is the shorter diagonal and this is the longer diagonal. So we're going to focus on this. Okay, and if this left visual helps you better, then we're going to talk about the green one, the green diagonal. Okay, this one. Okay, and there is no rocket science, and it's pretty straightforward. If you see this square at the bottom, all the sides are square. So if you take a big square here, okay, this is going to be x and this is going to be x in length, and we're going to talk about this diagonal. And we know that all the angles are going to be at right angles. We saw that in the beginning because it's a square, this is going to be right angle. So we know that this forms a Pythagoras theorem, and this becomes the hypotenuse of the Pythagoras triangle, right? So it's going to be simple that we're going to take a hypotenuse square. We know the Pythagoras theorem. Hypotenuse square is equal to squares of this both the sides, x square plus x square, or we can say hypotenuse is equal to root. We can introduce a square root and say x square plus x square, and if you solve that, it becomes 2x square. And if you take the square root of x square, it becomes x, and root 2 remains all by itself. And hence what we get is the length of the shorter diagonal is nothing but root 2 x units. Always remember that you have to add the units. If it's given in centimeter, you can say centimeter or meter. If nothing is given, just call it plain units so that you can get the full marks. So length of the shorter diagonal is root 2 x. Okay, we just applied a simple Pythagoras theorem. And let's take the same concept and try to apply it on a cuboid. Okay, let's go down. So in the cuboid, nothing changes. The only thing changes is a cuboid. This is a square. In the cuboid, each surface is going to be rectangular. Each side is going to be rectangle, and this is the cuboid. This is still a cube, but still, even for a rectangle, and we're not going to talk about this diagonal. We're talking about the diagonal, this diagonal. So that means it should be something of this sort, connecting this point and this point, the shorter diagonal. Okay. So if we take the bottom part where its length and breadth is given, and if we just take a simple rectangle, again it's the same story like the cube. We, instead of same values, we have a length and we have a breadth, and we still have this as a 90 degrees. So we can apply Pythagoras on this hypotenuse, which is a diagonal, and we can use the same logic, but instead of this time having both x squares or values to be same, we are just going to use length square and breadth square, and that will remain as it is. So in this case, the length of a shorter diagonal for a cuboid is going to be, let's say if we call this as a, okay, the shorter diagonal is going to be square root of length square plus breadth square, and again you put the units so that you don't forget that. So that's the only difference. Over here both the things are same, and both over here it's length and breadth. So if you remember one, you can always get the other one, and that's how I tell you, no need to memorize every formula, just get the clues and you'll be fine. Okay, now let's move on to calculating the length of the longer diagonal, this one. Like I said, the diagonal that crosses two different sides. Okay, and this is going to be always longer. In this case, we're talking about this. And again, let's talk about cube as the first example. Again, in this case, it's the same magic of Pythagoras, because from the above, we have already calculated the length of the green one, which is the face diagonal, as x square plus x square or root 2 of x, whatever you want to use. So this is going to be the length of this. And we know for a cuboid, all the sides are same. So if you see here, we have got the length of, we have got this, and we know this side also is going to be x. That is the side, the straight line connecting H and D is also going to be x. And if you look at this diagram or this diagram, this also forms a right angle. This also forms a right angle. The cube is tilted, but if you keep the cube straight facing you, you will see that the one in the orange forms a right angle with the one in the dot, which is the diagonal. So we have x and we have this measure here. So this diagonal or the longer diagonal is again going to be Pythagoras, and it might look tricky, but it's pretty simple. What we're going to do is we're going to take the whole length of this and square that, because we know that hypotenuse is equal to square root of side 1 square plus side 2 square, and we have the whole root. We know that, right? So if you see, this is side 1. The side 1 already has a square root. So this is side 1, the square root of that, okay? And we take the diagonal as it is, and we need to square it up like this. So we are going to square it up, and plus we are going to add this height or the other side, which is x, and that's going to be again squared because we have a square here. So that's going to be squared, and then we need to add a square root for the whole of this so that we get the length of the longer diagonal, which is the hypotenuse, and this particular outer square root is for the whole of that. So don't get confused between the outer square root and the inner square root. The inner square root is for this, because this whole thing is the length of one of the sides or the shorter diagonal, which we need to play. So that's the only difference. And once you open up, if you see here, if you open up this, let me get this So we have a square root and then we have a square. So what essentially happens is this square root gets out of the way and we just get whatever is under the square root. And if you add all of them linearly, we get 3x square. And then the square root of x square is x, and then root 3 becomes as it is. So it's a root 3 x units. So length of a longer diagonal for a cube is root 3 x units. Pretty much straightforward, okay? And that's an easy way to remember because the length of the shorter diagonal is root 2x, length of longer diagonal is root 3x. And if you remember that, it'll be very easy. And the same thing we apply for a cuboid. In the case of a cuboid, now we are going to calculate this shorter diagonal. In the last, from the text above, we calculated this one, which was a, which is what we got as square root of L square plus length square plus breadth square. So this and this, we got it. Now that has become the length of the shorter diagonal, which is also one of the sides of this triangle. If you see this this dotted line all the way, H, B and F. So this is kind of a rectangle over here, or you can say this is a rectangle over here. Like I said, think from not from the tilt standpoint, keep the cuboid straight and you will see that. So now our objective is to find a value of this, okay, D. And we again apply the same Pythagoras theorem, just like how I explained you. We already know assume that this is your first side. So we already know the length of this side, which is going to be L square plus B square. And because of the Pythagoras theorem, we need to add another square root and square this over here. And the other side is going to be the height, because it's a rectangle. We might have a different dimension. So we're going to take this height over here and we're going to square that out. And then finally take the square root of the whole thing, okay? And there is not going to be anything simplification. So all we get is this square root gets cancelled out because of this square, and we get just a linear term, which is L square plus B square plus H square, basically length square plus breadth square plus height square. And that's the length of the longer diagonal in case of a cuboid, okay? As simple as that. And like always, don't forget to add this piece units, okay? So that's pretty much simple. So what did we learn in summary before we wrap up, okay? No need to memorize all the formulas as much as possible. Just remember the visuals, okay? We're talking about a cuboid or a cube. If it's a cuboid, everything is in square shape. If it's a cuboid, if it's a cube, it's in square shape. And if it's a cuboid, it's a rectangle. That's the only difference. And if you're talking about shorter diagonal, which is this diagonal, it's a root 2 x units. And in this case, we are going to use the length square plus breadth square. So if you remember this, just let's say you just remember this, then you don't have to remember this, because you know that if you're going to switch to a cube, this L is equal to B, so it's going to be x square plus x square, or you can say L square plus L square, or B square plus B square, because all the lengths are the same, okay? So you can just remember this. Similarly, for the longer diagonal, you can think that it's root 3 by x, root 3 into x, sorry, or you can think from this standpoint where for the cuboid, you can remember this easily, and for the longer diagonal, you can add one more term, h square. And that way you don't have to remember for the cube, you can substitute all the values the same to get the answer. So whatever works for you. So try to minimize the number of formulas you're going to memorize, because mensuration, there are a lot of things coming up. So let's try to avoid memorizing everything and memorize only a few that is required, and rest, like I said, we will derive it on the fly. So that's going to be a wrap up on this topic, and then we will switch to the next topic.